Alright, welcome to section 11.1, Basic Sequences and Series. In chapter 11 we're going to be talking about all sorts of different things to do with sequences. We're going to be learning about sequences where you add or subtract to get the next term, and sequences where you multiply or divide to get the next term. And now today is just the basic introduction. So the sequences today, anything could happen. Adding, subtracting, multiplying, squaring, anything could happen, and today we're just going to introduce sequences. So a sequence is a collection of numbers in a certain order. A collection of numbers in a certain order with commas in between. Here's an example. 3, 6, 9, 12, 15 is a sequence. And now just so you know, the first number that comes in the sequence we're going to call term 1. And the notation we're going to use for term 1 is A sub 1. The second thing that you see in the sequence is called term 2, and we're going to use A sub 2. So if I kept going, I've got A sub 3, A sub 4, A sub 5 for the other three terms in this sequence. And the sequence that I just gave you is called a finite sequence. A finite sequence has a specific number of terms, or you know the last term. To make that into an infinite sequence, I would add a ... at the end. So an infinite sequence continues without stopping. An infinite sequence continues without stopping. And I've got, for example, 3, 6, 9, ... The ... means it's infinite. Unless, again, sometimes it doesn't actually continue to infinity if they specifically tell us that we're ending at term 100 or something like that. And then, I already said this, but each number in the sequence is called a term. Alright, so for the first example, I've just got a bunch of different sequences. Again, anything could happen. Adding, subtracting, multiplying, dividing. We're just going to try to identify the pattern and find the next term in the sequence. So look at the first one here, A. So it looks like it is adding 5. And so if it's adding 5, the next term in the sequence is 25. Now some of these are kind of tricky, but why don't you just take some time right now, think outside the box, pause a video, try a few of these, see if you can figure out what the pattern is. And when you are ready, hit the unpause button. Alright, I'm guessing that B and E were pretty easy for most of you, but maybe the other ones you didn't get. I don't know. Let's look at C. So you might be thinking, oh, it's not multiplying or adding to be anything specific. In this one, actually, though, the pattern is every time it's adding something that's 2 greater than the previous thing it added. So the next time I would add 12, making the next term 42. And I'm going to try to describe that in words. I'll say add 2 more than added previously. Now example D, you maybe saw the pattern but weren't sure how to describe it. So if you look, the top is just increasing by 1 each time, the bottom's just increasing by 1 each time. So if I was going to describe that in words, maybe I'll just say top and bottom increasing by 1 each time. And finally, F. This one's a little trickier, but look at this. The top number is being added by 2 each time, and the bottom number is being added by 1 each time. So the next term, plus 2 on top, plus 1 on bottom, would be 10/9. So I'm going to, again, try to describe it. Top added by 2, bottom added by 1. And again, sequences today, any old sequence. Anything could happen, because today we're just introducing things to you in general. For example 2, we're going to be given two different notations, and we're going to write the first 4 terms of the sequence. So here's what I mean. If I'm given this is called our sequence rule. I am going to find term 1, and when I find term 1, I plug in a 1 for n. Alright, and I find what that is. So 2 times 1 is 2 plus 3 is 5. And again, I don't have to say term 1 equals, because I can have mathematical notation for that. So a sub 1 means term 1, a sub 2 means term 2. So that's 4 plus 3, which is 7, and then I'm going to keep going. 2 times 3 is 6, plus 3 is 9. Term 4. So see how every single time I'm just plugging in the term number? It's kind of like creating a table of values. So there I go. There's my first 4 terms of my sequence. Now a few things that we need to be careful of here. If we look at example B, I wrote it in different notation, but we're still finding a sequence, so I can still say -1. Notice that when I have this, I want to do that thing in the exponent first, and notice that -2 is in parentheses. That makes a big difference. So my term 1 is actually 1. Now I'm plugging a 2 in, so I got -2 to the 2 minus 1 is 1, so -2. Few comments, just make sure you use parentheses. Make sure you plug things in correctly, and don't take shortcuts if you can help it. So let's see here. I end up with 4. Again, it's the -2 with parentheses. -2 to the 3rd is -8. Alright, hopefully you can see what I'm doing here. I put in a bunch of examples for this just because in these different situations, sometimes students can end up with incorrect answers by doing the wrong calculator entry. So just comment, when in doubt, use parentheses. That'll help. And then why don't you pause the video and try these, and I will show the answers. And then if you did not get the correct answer, we can go over it in class. So go ahead and pause the video, try 1 or 2 of these, and then check your answers. When you unpause, I'll have the answers showing. Alright, here's the answers for C, D, and E. And again, if you didn't get any of those correct, try to find your mistake. And if you can't find your mistake, please ask me about that in class tomorrow. So the next thing we're going to talk about today is something called a series. So I said that a sequence had commas in between. The reason I specified that is because a series has plus signs in between, and I'm actually adding. So a series is like a sequence, only with, so it is like a sequence only with plus signs in between. And you can have a finite sequence and an infinite sequence. So let me show you. And then just as a comparison, so a series specifically would look like this: 3 plus 6 plus 9 plus 12 plus 15. And because I have the pluses, I can also find the sum of the series. So I would add them all together. And that's just a review. The sequence had the commas in between. So a series has plus signs, and we can actually add it and find an answer for the sum. And the sequence is just commas. And I can have an infinite series. All I gotta do is put the plus signs in between and make the dot, 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 and just as a matter of comparison, there is again the infinite sequence. When you're finished writing that down, go ahead and turn to the back. I need to tell you about something here that is confusing. So we're going to be working a lot up on this a lot during class to make sure you understand, but we're going to learn right now about something called summation notation. So summation notation uses this symbol right here. That is a uppercase Greek letter sigma. You may have seen it if you ever drive by the U of M and you see the fraternity and sorority houses. Sigma is a letter that you'll see on some of the houses. It's a Greek letter. Sigma means we add. So if it just has a sigma, that means that we're going to be adding something together. And here is what each of these pieces mean. Please write this down. The number on bottom, or actually, well, we'll start with this little I right here. That I right there just tells us what variable we are using. What variable we are using. So sometimes it's going to be n, sometimes it's going to be k, sometimes it's going to be I. Doesn't really matter. It could change. You can use any variable you want. So that little number there just tells us what variable we're using. That letter tells us what variable we're using. This lower number right there is the lower limit. So right now it is a 1, so in my situation I would start at term 1. If this was a 3 right there, I would start adding at term 3. And if it was a 4 right there, I'd start adding at term 4. Then the number that's on top, and right now it's just a n, but it will be a number when you have an actual problem. That's the upper limit, so that tells me what term to stop at. So we have one more thing to say here, but let me just show you what I mean. For my example, I'm going to have k equals 1 to 5, and that means I start at term 1, and I'm going to stop adding at term 5. So I go from term 1 to term 5. That's what the top and bottom means. And then last but not least, this little part right here will always be the sequence rule or the argument. So it'll tell us what formula to use to find the terms. So I'll call it right now, maybe I'll call it a formula for the nth term. That's the official language for it, the formula for the nth term. And then this is me just, we would find all those terms and add them together. Alright, let me give you the rest of my example. The rest of my example is, right next to my sigma for my example, I have my formula is 3k. And my variable right now is k. Okay, so here's what this means. If it says I'm going to evaluate, and we're going to write the series and the sum. So the series is going to be me finding my terms from 1 through 5. And here I go. So term 1. I'm going to plug in a 1 into k. And then this is just my work right here. My actual answer is going to be down here, right? Okay, so 3 times 1 is 3. So term 1 is 3. To find term 2, I'm going to put a 2 in for k. That's 6. And again, I'm going to keep going until I get to term 5, because that's what my sigma notation tells me to do. So term 3, I plug in a 3. And that's 9. And I specifically made this the same series that we've been working on with our examples on the front page as well. So here you have a different notation for how to get the same series. And I'm kind of running out of space, so I'm just going to write it up here. But for term 4, I'm going to do 3 times 4. And that is 12. And for term 5, I'm going to do 3 times 5. So again, whatever the term number is, that's what you plug in for your variable. So that is called the series right there. That is my series. And if you actually add those together, you get 45, and that's considered the sum of the series. So if they ask you for the sum of the series, you add them all up and you get your number. So go ahead and pause or rewatch that if you need to. I'm going to show you 3 examples now before we move on with our next thing. For my first example, I've got term 1 up to term 6, and I'm finding 2i. Okay, so here I go. I like to kind of write out my work again. So I'm going to do term 1, term 2, term 3, 4, 5, and 6. And each time my formula is 2i. So each time I'm plugging in my term number in for I. So this one's actually pretty similar to what we just did. So 2 times my I. 2 times my term number, 2 times my term number. And for some of these you can kind of see a pattern forming, but I'll keep going the official way just so you kind of get the hang of it. So term 5 is 10, term 6, 2 times 6 is 12. So that is considered the series. See how it said write the series and the sum? That's my series. So 42 is the sum this time if you add all those together. Just type it into your calculator and add it. So again, go ahead and pause if you need to get all that down, and then let's look at example B. Make sure you watch example B because there's something new with this one that I need to show you. Alright, the new thing I need to show you is this one is not starting at term 1. So we need to be careful here. This one starts at term 3. And then it ends at term 6. So for this one, I'm just finding term 3, term 4, term 5, term 6. I don't have to find terms 1 and 2. And notice my formula, 2 plus I squared. So to figure this out, 2 plus my variable squared. So 2 plus 9, 11. 2 plus my variable squared. So 2 plus 16 is 18. 2 plus my variable squared. 2 plus 25 is 27. And 2 plus my variable squared, 2 plus 36 is 38. So that's my series. The sum of the series this time is 94. Alright, look at C. First I want to notice that C is starting at term 2 and going up to term 10. Why don't you go ahead and try this one on your own and see if you can get the correct answer. So go ahead and pause the video and try part C, noticing that it just starts at term 2, so don't start at term 1. And then when you unpause, I'll have the answer showing. Alright, here is the series. Just notice that if I had a fraction, I reduced it to get my answer for the series. And then when I added all those together, it ended up being this decimal 3.86, which if I changed that to fraction form, it was actually 4,861 over 1,260. So in this situation, actually leaving it as 3.86 might really make more sense, but that is the sum. All right. To end up our lesson today, I've got some special shortcuts to show you. And now using these special shortcuts is optional. You don't have to use these. So if you, because this isn't going to be on a formula sheet or anything, so if you don't have these memorized, just write it out like I just did for example 3. That's the way to do it longhand. But here's our examples. If I have in summation notation I to n and my formula is 1, the answer is just n. By the way, these 3 special shortcuts I'm about to show you only work if the starting term is 1. Alright, so for example, if I was trying to find the sum of j equals 1 to 8 of 1, the answer is 8. And by the way, this one seems a little weird, but if you don't have a n or a variable right here, that just means that every single term is that number. So what's happening here is I'm taking all of those, all of them are going to be 1s, but I add all those together, 1 plus 1 plus 1 plus 1 and so on, and that's how I get 8. So for example, this one would be equal to 6. And when I say n, I mean this number on top. So the second special formula is if I have I right there, and that's my variable, if it's just a plain I, this is equal to n times n plus 1 divided by 2. And that, when I say n again, I mean the number on top. And again, this is a shortcut formula that you can or cannot use. So if you don't want to use this, just write it out like we did in example 3. Here's my example. If I have this, again, just a plain variable there, no number in front, nothing squared or anything. So I'm going to do 5 because n is 5. And then in parentheses, n again, plus 1. all over 2. So that is equal to 5 times 6 over 2, or 30 over 2. My sum is 15. And now that's the same thing you should get if you found each term and added it together. The last shortcut I want to show you today is if you have a I squared next to your summation, the formula for the answer of the sum is this. On top of a fraction bar, I've got n times n plus 1 times 2n plus 1. On bottom of the fraction bar is a 6. Alright, so I got 2 examples to show you. First example, n is 10. So 10. 10 plus 1. 2 times 10 plus 1, and then that's all over 6. Alright, so that's 10. 10 plus 1 is 11. 2 times 10 is 20, plus 1 is 21. And you end up with 385. And then let me show you what to do if you have a number in front. So if I had a number in front, I'm still going to use my formula. I'm just going to have a 3 in front of the whole formula, so everything else is going to be the same. So I'm still going to put in my n plus 1, 2 times n plus 1. Just I put a 3 in front. So this 3 directly just stuck on there, and then everything else fine as normal. So basically I found the sum using the formula, then times by 3. Now again, if you don't like those formulas, you don't have to use them. That's all I've got for you today, so make sure you write down your questions and talk to me in class about anything you need to. Thanks for listening.